Hi everyone. Today we're continuing with Chapter 3 and we're looking at Section 3.2. The title of the section is Empirical Rule and Z-scores. And in this section we're really going to focus on other ways we can analyze symmetric distributions. So that's really our focus in this section is symmetric distributions. So first of all, what is the empirical rule? If the shape of the data distribution is approximately unimodal, so I'm going to fill that in here, so unimodal, and symmetric, I'm going to abbreviate, didn't leave you much room here, but symmetric, that's really the key characteristic, then we would expect that roughly 68% of the data to be within one standard deviation of the mean, and 95% of the data to be within two standard deviations of the mean, and 99.7% of the data to be within three standard deviations of the mean. And for that last one, you can really say pretty much all of the data, unless you've got some really strange outliers, all of the data, for the most part, should lie within three standard deviations of the mean, if we're talking about a distribution that's unimodal and symmetric. So if you remember from the last lesson, we had a distribution of smog levels in a sample of cities. The graph of it's below for you here, and you can see that this was a symmetric and unimodal distribution. And so the mean smog level, they told us, was 8.3 micrograms per cubic meter, and the standard deviation was 2.36 micrograms per cubic meter. So I'm going to write down just a couple of notations. So in a sample, the mean, remember we use X bar to represent the mean, and that's 8.3. And then the standard deviation, remember in a sample we use a lowercase s to represent the standard deviation, and that's 2.36. So the empirical rule gives us an idea of where the data should lie in the distribution based on where it falls as far as distance-wise from the mean, how many standard deviations from the mean. So the empirical rule in this example will tell us that about 68% of the cities will have smog levels that lie within one standard deviation of the mean. So what do we mean by that? We mean one standard deviation below and one standard deviation above. So for this first Roman numeral 1 here, the way we're going to figure this out is we're going to say, okay, the mean is 8.3, and we're going to add and subtract one standard deviation of 2.36. So if we think about 8.3 minus 2.36, that gives us a lower bound. I'm going to use a parentheses here to represent the bound of 5.94 and an upper bound of 10.66. How am I getting those numbers? So 5.94, we did 8.3 minus 2.36 for the lower bound. 10.66, we did 8.3 plus 2.36 for the upper bound. That means that not 68% of the cities in this sample should lie somewhere between those two pollution levels. So like 5.94 maybe is about right here. 10.66 maybe about right here. And so 68% of our data is going to lie between those two numbers. 95% of the data will lie within two standard deviations. That's what the empirical rule tells us. 95% lies within two standard deviations. So there's a couple ways we can do this. We can either start at 8.3 again, and we can say 8.3 plus and minus 2 times the standard deviation of 2.36. Another way of thinking about it is just to say, okay, well, we've already got one standard deviation below and one standard deviation above. And so what we can do is take those numbers from part Roman numeral 1 and just add and subtract one more standard deviation. So in other words, 5.94 minus 2.36 would put us at 3.58, and then 10.66 plus another standard deviation of 2.36 puts us at 13.02. So in terms of our sample, that means 95% of the cities in our sample should be between those two levels of smog. Graphically, let's see, so I'm thinking 3.58, I'm just kind of estimating, is somewhere right in here. 13.02, again, just estimating, somewhere right in here. So 95% of the cities in my sample should lie between this number and this number. almost all of the cities will have smog levels within 3 standard deviations. Technically, it's 99.7 and some change percent, but for estimation purposes, it's almost all of the data, almost 100% of the data. So again, we can go back to the 8.3 and we can add and subtract 3 standard deviations, or we can take the previous value of 3.58, subtract 1 more standard deviation for the lower bound, we get 1.22, add a standard deviation to the upper bound, we get 15.38. And so that means in terms of our sample, almost all of the data is between those two numbers. And I'm thinking, I'm kind of estimating right about here. So that's all of this data. So all of these cities are going to be lying with smog levels between 1.22 and 15.38. So that's 99.7 are pretty much all of the data. We've got a few out here, 1 or 2 out here, but most of it's going to lie within those two numbers. Part B says apply the empirical rule to the histogram of the distribution of the data below. I've kind of already done that. My picture's looking pretty messy here, but if you will go through and just kind of label each of those little tick marks where those 1, 2, and 3 standard deviations out are, you'll see it. All right, so let's look at the next example. Suppose that the daily average temperature of city A has a mean of 65 degrees Fahrenheit with a standard deviation of 8 degrees. When I approach a problem like this, I like to write those down using the correct notation. So I'm going to come over here and just jot that down. So X bar is going to be, let's see, this we're looking at daily average temperatures for a city. The mean temperature is 65 degrees, and lowercase s, standard deviation, is 8 degrees. Determine the temperature ranges for 68, 95, and 99.7% of the data. So 68% of the data should lie within 1 standard deviation. So I'm going to do 65 minus 8 and 65 plus 8. And so that gives me a lower bound of 57 degrees and an upper bound of 73 degrees. So 68% of the days over the course of a year, or whatever sample we looked at to get this information, for the city are going to have temperatures between 57 and 73 degrees. 95% of the temperatures are going to range within 2 standard deviations. And so since I just did 1 before it, I'm going to subtract 8 again. So I get a lower bound of 49 degrees and an upper bound of, 81 degrees. And then finally, 99.7% of the data, and I'm going to have a space here, so I'm going to erase this for now. Let's come over here and write it. 99.7% of the temperatures, the daily temperatures, are going to lie within 3 standard deviations. And so take your previous values and subtract the standard deviation from the lower bound. That puts me at 41 degrees. And the upper bound, that puts me at 88 degrees. Let's write that again. 89 degrees, there we go. I forgot what the standard deviation was. All right, so almost all of the city's temperatures over a given year or whatever sample we pull are going to lie somewhere between 41 and 89 degrees. So part 2 here is a really important question, and we're going to be doing a lot of that this semester in terms of looking at whether or not something is unusual. And when we have a symmetric distribution, one way to decide whether or not something is an unusual temperature, so that's what they're looking for, decide whether it is unusual to have a day where the temperature is colder than 49 degrees. Well, our cutoff for what's considered unusual is going to be anything outside of 2 standard deviations. So our cutoff is anything that's outside of 2 standard, I'm abbreviating, standard deviations. And that's just kind of a general rule because 95% of the data is within 2 standard deviations. So statisticians usually use 2 standard deviations as a cutoff when we're looking at a symmetric distribution for what's unusual. So the question is 49 degrees unusual? I would say, and actually let's be careful how they phrase it. They said colder than 49 degrees. So since they said anything colder than 49 degrees, in other words, below 49 degrees, we're going to say yes. Where am I getting that from? Well, for 2 standard deviations, the lower bound was 49 degrees. So colder than that would be outside of those 2 standard deviations. So yes, since colder would be outside of 2 standard deviations. And that's what we're looking for. So remember that two standard deviations is going to be our cutoff. All right, let's look at z-scores and what we mean by a z-score. So a z-score of a data point, so if you have a point in your data, say a temperature that we pull for the city in the previous example, or a just any smog level for a particular city in our sample, any particular data point, the z-score for that data point is the number of standard deviations, and I apologize, I didn't leave you much room here, standard deviations from the mean that the data point is, I'm going to say located. I'm going to add that word to the end of that sentence. So the number of standard deviations from the mean that a particular data point is located, that's called its z-score. The formula for computing the z-score is given by this formula. So z is equal to x minus x bar divided by s. X bar is the particular data point that we're looking at. So whatever point we're interested in, whatever piece of data, that's x. X bar, remember, is the mean, and S, remember, is the standard deviation. So what does a z-score, for example, of 2.1 mean? So a z-score of 2.1 means that the observed data point, whatever it is we're looking at, I'll say data value, is, and z-scores can be negative. So a z-score of 0, let me mention that. So a z-score of 0 means that you're at the mean. So it's kind of like a number line. 0 is right in the middle where the mean is. So a positive z-score means that you are above whatever the mean is for that particular sample. So a z-score of 2.1 means that the observed data value is 2.1 standard deviations above the mean for that particular sample, or for that particular data point. A z-score of negative 2.1 means that you're below the mean, because remember, z-score of 0 is right at the mean. So negative means you're below the mean. So that means the observed data value is 2.1, let me write that a little nicer, 2.1 standard deviations. You know, and you can abbreviate. I'm writing DEV to be emphatic, but if you want to put SD for standard deviations, that's fine. Below whatever the mean is for that particular data. So a negative z-score means you're below the mean. A positive z-score means that you are above the mean. So let's look at a practical example. Sort of the big picture, the point of using z-scores is to give us a way to compare different distributions. So I may have one sample or one distribution where the mean is one value and the standard deviation is something else, and another sample with a different mean and a different standard deviation, and I want to make comparisons between the two. Z-scores give us a way to do that. And here's an example of that. Suppose that I-95 has a mean speed of 60 miles per hour with a standard deviation of 5 miles per hour. And I-80, so different interstate altogether, has a mean speed of 60 miles per hour but a standard deviation of 10 miles per hour. So let's make some notes here. So I-95, let's write some things down. So for I-95, the mean speed is 60 and the standard deviation is 5. For I-80, so a different distribution altogether, oops, I wrote 90, I-80, a different distribution, happens to have the same mean, although it doesn't have to, but in this case it does, but it has a different standard deviation. So the standard deviation is larger for I-80. That means the cars are going to be more spread out. Their speeds are going to be more spread out if we pull a sample of them. So the question says, is a driver who is traveling 70 miles per hour on I-85 traveling faster or slower relative to a driver driving at the same speed on I-80. So what we're going to do is we're going to take that same driver who's going 70 miles per hour on both roads, and we're going to calculate the z-score. So I'm going to call, I'm going to call I-95 distribution A, and I'm going to call I-80, I'm going to call that distribution B. So the z-score for the driver on distribution A, I-95, we're going to use the formula above, so we're going back to this formula. So the formula is x minus x bar divided by s. So x is his particular speed, so that particular data point of 70 miles per hour, minus x bar, which is the mean on I-95, divided by s, which is the standard deviation on I-95, which was 5. So 70 take away 60 is 10. 10 divided by 5 is 2. On I-80, the z-score, let's calculate his z-score. So on I-80, I'm calling this distribution B. I'm just using A and B. That's not part of the computation. I'm just using that to identify which is which. Distribution B, so on I-80, it's the same speed of 70 for the driver. It happens to be that the mean is the same, although it doesn't have to be, as the previous interstate. But this time the z-score, I'm sorry, the standard deviation is 10. So 70 minus 60 is 10, divided by 10 gives us a z-score of 1. So relative to the rest of the drivers on the road, which one seems like he's going at a faster speed? They're both going 70, but compared to everybody else on the road, which one is going at a faster speed? If we think about it visually, on I-95, so remember that was distribution A right here. On I-95, the z-score for the mean, of course, would be right in the middle. If he has a z-score of 2, that means the driver is up here. So he is traveling faster than 2 standard deviations above the mean. Or his speed, I guess, is 2 standard deviations above the mean. All of these drivers are going slower than him. On the other interstate, the mean is still right in the middle at 0, but his standard deviation is only 1. So which one of these is he traveling faster compared to the other drivers? Hopefully you see that it's on I-95, this guy right here. This guy right here. He's got a higher z-score. That means he is 2 standard deviations above the mean, compared to the driver on I-80, who was only 1 standard deviation above the mean. So I'm going to erase this picture because I'm a little bit short on space here, but let's write out what we just said. So the driver who is relatively faster, oops, let me not use that color. Let's go back to red. So the driver who is going to be relatively faster on I-95, since he has a z-score on that road of 2 compared to the driver on I-80, which only had a z-score of 1. All right, let's take a look at one last example looking at z-scores. So we're looking at test scores as an example. So Alice scored 80 on her first exam and 85 on her second exam in MAT223. On the first exam, the mean of the class was 70 with a standard deviation of 10. So I'm going to start jotting some things down here. So on the first exam, the mean of the class was 70, but the standard deviation was 10. On the second exam, things shifted a little bit. So on the second exam, the mean for the second exam was 80. So the entire class went up. The mean went from a 70 to an 80. But there was less spread in the second exam because the standard deviation was only 5. So the scores were closer to the 80% on that second exam than they were to the 70% on the first exam. So let's compute her z-scores for each exam. So for exam 1, I'm going to call this z-score 1. We're going to take her score, which was 80, and we're going to subtract the mean of 70, and we're going to divide it by the standard deviation of 10. So 80 minus 70 is 10. 10 divided by 10 is 1. On the second exam, she did a little bit better, but here's the catch. So did the rest of the class, right? Because the mean went up and the standard deviation, well, really because the mean went up. That's the main thing you want to look at there. So we're going to take her score on the second exam, which was 85. We're going to subtract the mean of 80. We're going to divide it by the standard deviation of 5. So 85 minus 80 is 5. 5 divided by 5 is 1. So yes, she did better on the second exam, but so did the rest of the class. So on which exam did she perform better compared to the rest of the class, compared to the entire class? Since she scored 1 standard deviation above the mean on both exams, we'll say that she scored equally well compared to the class. And so that's basically what a z-score, z-score does, is it gives you a way to compare two different distributions.